Welcome to AI Journal Club, the Digital Pathology Podcast segment where we take a closer look at the research shaping AI in pathology. This episode is one of our AI-powered summaries series, AI-generated deep dive into a paper worth your attention. It's curated from our weekly DigiPath Digest live stream that I run every Friday morning. I'm Dr. Alex Zhurav, and this is your shortcut to staying current. Let's dive into it.
What if you could accurately stage a patient's breast cancer without ever really zooming in enough to actually see the cancer cell?
Yeah, right. Like a blurry, high-altitude snapshot holding literally everything an AI needs to know.
Exactly. I mean, it sounds crazy, but welcome back, Trailblazers. Welcome to another Journal Club deep dive on the Digital Pathology Podcast.
It really does sound like a contradiction in terms, though, considering how much our field relies on just extreme magnification to find those really tiny cellular anomalies.
It does, because usually when we discuss tissue pathology here, there's this sort of expectation of microscopic precision, right?
Oh, absolutely.
We're looking for tiny mitotic figures, individual nuclear shapes, basically the absolute smallest clues to determine just how advanced a cancer is. But today we are looking at a paper that flips that entirely on its head.
Yeah, it challenges this core assumption that, we've all essentially just taken for granted, the idea that higher resolution is always a prerequisite for higher accuracy.
Right. Okay, let's unpack this. Because for our mission today, we're reviewing a really fascinating 2026 paper from the journal Pathology Informatics.
A great journal, by the way.
Oh, totally. And the paper is titled Deep Learning-Based Breast Cancer Stage Prediction from H&E-stained Whole Slide Images in Resource-Constrained Settings.
Quite a mouthful.
It is, yeah. Lead authored by Zsolt Bajcsy, alongside Biricz A Knudsen and their team, and their core question is just a total paradox.
Yeah, they want to know if an AI can accurately predict pathological TNM stages, so stages I through 3, for breast cancer using whole slide images at just 2.5x magnification.
Right, and for context, for our Trailblazers, the clinical standard is usually, 20x to 40x?
Exactly, 20x to 40x is standard.
Yeah.
So dropping a 2.5x, what's fascinating here is that it's a profound reduction in data.
It's massive.
They are intentionally blinding the algorithm to the microenvironment and just asking it to diagnose based purely on the macroenvironment.
And to understand why they would even attempt this, we really have to talk about the massive silent bottleneck in digital pathology right now, which is compute power.
Oh, yeah. The elephant in the room.
Seriously. High-resolution whole slide images are just absolute data behemoths. Scanning, storing, running AI inference on 40x images requires, massive server racks.
Incredibly expensive GPUs, too.
Right. And network bandwidth that, frankly, most community hospitals just simply do not have.
No, they don't. And that reality is leaving a lot of resource-constrained clinics completely behind in this whole AI revolution.
Exactly.
And that's the real driving force behind this study. The researchers aren't trying to build, some heavyweight multimodal AI model to squeeze out a tiny fraction of a % of accuracy on a supercomputer.
Right. We see enough of those papers.
We do. We see them every week. But instead, they're trying to build the most efficient, globally accessible baseline model possible using just primary tumor tissue. Their goal is a diagnostic tool that can run on a single consumer-grade GPU. Or, even just a standard computer processor in a clinic without $1 million IT budget.
Which is so needed. So let's talk about the math of this 2.5x magnification gamble.
Let's do it.
At standard 40x magnification, you are looking at around, 0.25 micrometers per pixel.
That's right.
So you see the individual cell morphology beautifully, but drop that down to 2.5x, and you're at roughly 4.0 micrometers per pixel.
Which sounds like a small shift when you say the numbers.
It does, yeah. But we are talking about exponential reductions in data volume here.
Oh, absolutely. Consider the extraction process. When you pull fixed-size image patches from a slide to, feed into an AI, operating at 2.5x means you extract 256 times fewer patches than you would at 40x.
Wow, 256 times fewer.
Right, and even compared to 20x, it's 64 times fewer patches.
That is wild.
So you're instantly bypassing those massive disk read and write delays, you're slashing your storage footprint, and you're drastically cutting the processing time.
It's basically like trying to identify a specific type of forest.
Okay, I like that.
Right. Like at 40x, you were standing right there in the woods looking at the veins on the individual leaves and, the texture of the bark.
Right.
But at 2.5x, you're basically looking out the window of an airplane at the overall shape of the canopy and the density of the tree line.
That's a really good way to visualize it.
But here's where I struggle with this a bit. Pathological staging, pTNM, right? Tumor size, node involvement, and metastasis. Staging inherently relies on seeing those leaf veins.
Traditionally, yes, it does.
Pathologists look for cellular atypia. They look for mitosis. If you go to the airplane view, everything is just a blur. So aren't they essentially just asking the AI to guess?
Well, not at all, actually, because they're relying on a completely different set of biological signals.
Okay.
The hypothesis is that the macroscopic features, the ones visible from that airplane view, they actually correlate heavily with the cancer stage.
Like what kind of features?
Things like the overall tumor growth patterns, the broad tissue architecture, and the way the surrounding stroma is physically reacting to the invasion.
Oh, I see.
Yeah. If that architectural disruption alone holds enough information to classify stages I and the third, it basically proves you don't necessarily need the microscopic leaf veins to know it's a diseased forest.
That's fascinating. So if we accept this blurry 2.5x view as our input, how does the AI compensate for the missing microscopic data?
It's a great question.
Because it must need, a completely different kind of brain to process that, right?
It does. The underlying feature extractor, the brain as you called it, has to be incredibly sophisticated.
Yeah.
Because you're starving the algorithm of raw, high-resolution data, its ability to interpret those broader spatial patterns has to be pretty much flawless.
And the researchers tested a few different brains for this, right?
They did. They started with a standard ResNet 50, which they fine-tuned on breast cancer images.
Okay, sure.
But then they brought in the heavy hitter, a foundation model called UNI, specifically a version they fine-tuned called UNA-FT.
Here's where it gets really interesting for me. Because I know ResNet is it's an older convolutional neural network.
Right.
And UNI is a vision transformer trained on over 100 million pathology images.
Yes. A massive data set.
And I hear the word transformer thrown around all the time lately as the ultimate solution for literally everything.
Yeah.
But why specifically does a vision transformer outperform a convolutional network on a blurry, low-res image?
Well, it really comes down to how they parse visual information.
Okay.
A convolutional network like ResNet processes an image by basically sweeping a small mathematical filter over local groups of pixels.
Like a magnifying glass moving across a page.
Exactly. It's very good at finding local textures and edges. But it really struggles to connect a pattern in, say, the top left corner of the image with a pattern way down in the bottom right.
It loses the big picture.
Right. A vision transformer, however, uses self-attention mechanisms across the entire image patch simultaneously.
So it takes it all in at once.
Exactly. It maps long-range dependencies. So it can understand the broader spatial context of that 2.5x blur far, far better than a convolutional network ever could.
Okay, that makes total sense. But wait, UNI has already seen 100 million high-res images.
Yes, it has.
It knows what human tissue looks like better than almost anything on Earth. So why did the team need to fine-tune it on a completely separate data set?
You mean the BACS data set?
Yeah, BSES, which only has, a few thousand patches of breast lesions? If UNI is already a genius, why send it back to kindergarten?
That's a fair point. But it's because it's a genius trained on a different visual reality.
What do you mean?
UNI was primarily pre-trained on 20x whole slide images. Showing it 2.5x images is literally like making it look through someone else's really thick prescription glasses.
Oh, wow. Okay, so it's disoriented.
Exactly. So fine-tuning it on the BSCS dataset, which, by the way, contains 7 distinct categories ranging from normal benign tissue all the way to invasive carcinoma, it does 2 vital things.
Okay, what are they? First, it forces the model to specialize its vocabulary specifically for breast histopathology.
Right.
And second, and this is the more important part, it aligns the model's internal representations to that specific low magnification airplane view.
Got it. And looking at the data from the paper, the fine-tuned UNI, the UNI-FT, it absolutely crushed the base UNI and the ResNet 50 across all the classification metrics.
It wasn't even close, really.
But we have to address how they actually synthesize this data. Because a patient's biopsy slide isn't just one neat little square patch, right?
No, not exactly.
It's this chaotic collection of thousands of them. So how do they turn thousands of blurry patch predictions into one definitive stage for the patient?
Right. So they feed those extracted features from the patches into an attention-based multiple instance learning model.
An MIL.
Yes, an MIL.
Oh, the puzzle bag analogy. I love this concept.
That's right, analogy, yeah.
So for our Trailblazers listening, imagine you have this massive bag of puzzle pieces, and that bag represents the whole tissue slide.
Not every piece actually shows the tumor. Some pieces are just, normal fat, or maybe empty white space on the glass, or just healthy connective tissue.
Exactly. And older algorithms would basically just mathematically average all of those puzzle pieces together.
Which seems terribly inefficient.
It is, because it waters down the critical cancer data with completely irrelevant background noise.
But the attention mechanism fixes that, doesn't it?
It does. It allows the model to assign a specific mathematical weight to each piece in the bag.
Oh, okay.
So it actively learns to ignore the fat and the connective tissue, and it heavily weights the regions of the low-res tumor that actually indicate the cancer stage.
So it's basically learning where to look before it even makes a decision.
Exactly. And that targeted weighting is exactly what allows the model to extract such high performance from such low quality inputs.
Which is brilliant in a controlled environment.
Always a caveat.
Always. Let's step out of the computer lab and see how this holds up in the wild.
Yeah.
Because we all know algorithms love to fail the second you test them on unfamiliar data.
It's the classic machine learning problem.
Right. So the team trained this UniFi-ML model on an internal data set from Semmelweis University. It was about 286 patients.
Yep.
And on their internal test set, it achieved a ROC-AUC of 0.663. Now, just real quick for our Trailblazers, ROC-AUC measures how well a model distinguishes between classes. 1.0 is perfect, 0.5 is basically a coin toss.
Exactly.
So 0.663 is a very solid baseline considering the extreme low resolution we're working with here.
It is. It proves the concept is viable. But of course, the ultimate test of any medical AI is the external validation cohort.
And this is where the paper completely threw me for a loop.
Oh,
yeah. Because they tested it on an external data set called the Nightingale cohort.
Mm-hmm.
It's this massive collection from the Providence Hospital Network with over 9,000 slides.
Huge.
Massive. And the model actually performed better on it. It hit an ROC-AUC of 0.672.
Right.
I don't understand that. Usually, an AI degrades when it leaves its home hospital. Did they accidentally leak Nightingale data into the training set? Because otherwise, that kind of breaks the rules of machine learning, doesn't it?
Well, no accidental cheating here, I promise.
Okay, good.
The reason it performs so well in that external data set is actually due to a masterclass in unsupervised data cleaning before the model ever even touched the slides.
What do you mean?
Well, think about it. With 9,000 slides, the researchers couldn't manually review every single one to ensure it was a clean primary tumor sample.
Right. That would take years.
So they built a quality control pipeline using TSNE and DB-scan clustering.
Ah, right. The sorting algorithm.
Yes.
It's like dumping a massive bucket of unsorted Lego bricks on the floor.
Exactly.
And instead of a human sorting them out, a robot automatically pushes all the red bricks into one pile, the blue into another, and then just tosses the broken pieces straight into the trash.
That's exactly how it works. They took the mathematical representations of the slides, plotted them on a visual map, and the algorithm just naturally clustered them.
And what did they find?
In doing so, they found these little clusters of slides that were actually just lymph node tissue or maybe out-of-focus smears or even just pen marks on the glass.
Oh, wow. Just garbage data.
Yeah. And the pipeline automatically deleted 3,340 bad slides without a human ever having to look at them.
That is incredible.
It really is. And that pristine, highly curated input is exactly why the model performs so well on the Nightingale cohort.
Okay, that makes a lot of sense. But then they tested it on a second external data set, the TCGA BRCA data set.
Yes.
And its performance dropped down to 0.632. So if they cleaned the data so well with the first one, why did it stumble there?
Well, because TCGA represents the absolute nightmare scenario for an algorithm.
Really?
Yes, severe domain shift. Because every hospital prepares their tissue slides slightly differently.
Right, so it's kind of like asking an algorithm that was trained to read handwriting written with a fine point ballpoint pen to suddenly read handwriting done with a thick, bleeding felt tip marker.
That's a perfect analogy.
Like the letters are the same, but the visual texture is completely alien to it.
That's exactly it. The TCGA dataset is incredibly heterogeneous. It's pulled from multiple institutions.
Oh, so it's a mix.
A huge mix, meaning you have different chemical stains left on for different amounts of time, making some slides intensely purple and others just faintly pink.
Right, I've seen that.
But the biggest hurdle is that TCGA mixes standard formalin-fixed paraffin-embedded tissues, the wax blocks we use every day, with frozen sections.
Frozen sections?
Yeah.
Like intraoperative rapid freezing?
Yes, exactly.
Oh, wow.
And consider the physical reality of a frozen section. You are rapidly freezing the tissue, which causes the water inside the cells to expand into ice crystals.
Which damages the tissue.
It literally tears the cellular architecture apart, and then it's sliced thicker than a wax block, which often creates folds and artifacts.
That sounds like a mess.
It is. Under a microscope, a frozen section looks fundamentally different, much messier, more distorted than a carefully preserved wax block.
Yeah, definitely.
So if your AI learned what cancer looks like on pristine wax blocks at Semmelweis, throwing a blurry 2.5x frozen section at it is just a massive domain shift. Frankly, it's impressive the ROC-AUC only dropped to 0.632.
That is a really fair point. Okay, so the TCGA dataset proves the AI struggles with messy, real-world preparation.
It does.
Let's look at what that actually means for patient care, though, because we need to look at the confusion matrix, where the AI's predictions matched reality and where it failed.
Right.
Because the model really struggled with stage 2 breast cancer. It frequently misclassified stage 2 cases as either stage 1 or stage 3.
Well, biologically, stage 2 is the messy middle.
Yeah.
It's a transitional phase where the tumor might exhibit features leaning toward early-stage confinement, or it might be leaning toward late-stage aggression. I mean, even a panel of human experts will frequently disagree on borderline stage 2 cases.
Sure, humans disagree all the time. But what scares me here is what the authors call serious understaging.
Ah, yes.
This is when the true label is an advanced stage 3 cancer, but the AI predicts it as an early stage 1.
Which is obviously a major error.
Huge.
Yeah.
And this happened in 7% of the internal cases, 15% of the Nightingale cases, and a massive 20% of the TCGA cases.
Right.
So what does this all mean? If it's missing advanced stage 3 cancer 1 out of 5 times in a diverse data set, I clearly can't use this to diagnose my patient today. It's just too dangerous.
The authors are completely transparent about that, and they emphatically agree with you.
Okay.
They explicitly frame this tool as a WSI-only baseline. It is not designed to replace conventional clinical workflows, and it certainly doesn't replace human pathologists.
Thank goodness.
Its true value lies in triage and in retrospective cohort analysis.
Okay, so we aren't replacing the microscope at all. We're basically giving clinics an automated sorting hat for incomplete medical records. Imagine a community hospital has a biobank of, say, 50,000 slides from the last 20 years, and half the digital files are missing their staging data entirely.
Which happens all the time.
Right. So instead of throwing that vital research data out or paying a team of pathologists for 3 years to manually review them, you just run this 2.5x algorithm on a basic computer overnight.
Precisely. It rescues dark data. And for prospective clinical deployment, it basically acts as a safety net.
Okay.
But to use it safely, the paper recommends a critical step: local recalibration of decision thresholds.
You mean tuning the AI?
Yes, tuning it. Because AI models output probabilities. They essentially say, I am 70% sure this is stage 3.
Right.
A hospital doesn't have to accept the default settings. Since serious understaging is the most dangerous clinical error, a hospital can tune the algorithm exactly like you would tune a smoke detector.
Make it hypersensitive.
Exactly. They can lower the threshold for stage 3. They might configure it so that if the AI has even a 30% suspicion of stage 3, it automatically flags the slide and routes it to a senior pathologist for immediate manual review.
That makes so much sense.
Yeah.
It's really about designing the clinical workflow around the tool's known limitations, rather than pretending the tool is somehow flawless.
Exactly.
And doing all of that triage and sorting with a fraction of the computing power, storage space, and scanning time that we previously thought was necessary.
It's a phenomenal proof of concept for global health equity, really.
It really is.
But I want to leave our Trailblazers with a final thought to mull over, because there is one finding in this paper that is truly haunting in the best possible way.
Oh, I like the sound of that. Let's hear it.
Well, remember that staging breast cancer isn't just about measuring the size of the primary tumor, right?
Right, the T in TNM.
Yes, the N in pTNM stands for node involvement, whether the cancer has actively spread to the regional lymph nodes. Now, consider the data they used. The model was fed only images of the primary breast tumor.
Oh.
In fact, they used that TSNE clustering pipeline we talked about to explicitly find and delete all the lymph node slides from the Nightingale dataset before they even started training.
Right, they scrubbed them completely out.
Completely. Yet, the model was still able to predict the overall stage, which inherently includes that distant lymph node status, with a statistically significant degree of accuracy.
Wait, really?
Yes, it predicted whether cancer had invaded the lymph nodes without ever looking at a lymph node.
That is wild.
It deduced metastasis purely from the architectural disruption and the growth patterns of the primary tumor itself.
Wow.
So my question for you and for the listeners is this. If a blurry, low-resolution snapshot of a primary tumor holds the secret to distant nodal metastasis, what other macroscopic systemic secrets are hiding in plain sight on our daily H&E slides, just waiting for the right algorithm to notice them?
Oh, wow. That seriously gives me chills.
Why?
It means the answers might literally be right there in the shape of the forest canopy. We just haven't known how to read the trees yet.
Exactly.
Well, Trailblazers, thank you as always for joining us on the Digital Pathology Podcast for this deep dive. Keep questioning the standard resolution, keep looking at the bigger picture, and keep pushing the boundaries of medicine. We'll catch you on the next deep dive.
That's it for this AI Journal Club episode. If you want more like this, make sure you're subscribed to the Digital Pathology Podcast and come join us for the DigiPath Digest, our weekly live session. During these live streams, you can vote which paper becomes an AI deep dive. And if you're serious about digital pathology, grab my free book at digitalpathologyplace.com. This is the best place to start your digital pathology journey. Thank you so much for listening, and I'll talk to you in the next episode.